So how do we get this? Well, by definition, we know that box psi equals not eventually not psi. For now you look at the law for eventually psi, you plug this in for eventually not psi, so what we get is not psi, or next eventually not psi. That's exactly what we get here. Now you can push in the negation inside, just De Morgan. So we get not psi and not next eventually not psi. And now you can, of course, simplify this to psi, and you can push this negation inside. Why can you push this negation inside? Because of this law that you can push this negation in there. So if we do this, then exactly we get psi and, well, I did not push the negation yet. I do that now, so now you push the negation in, and now you see this is exactly the formula that we started with here on this side. So we can replace this part by box, and therefore you get this formula. Good. Now, what's the specific thing about these equivalences? The specific thing is that the formula on the left-hand side also appears on the right-hand side. You see this here, eventually psi occurs also here. I mean, nested in terms of the next operator, but you see the same operator occurs there. So that means that in principle, you could apply the equivalence again on this subformula. But then again, you get a subformula of eventually psi. You can apply the equivalence again and again and again and again, right? And then the question is, where does it stop? What is the interpretation, basically, of the eventually psi? And mathematically speaking, this means that these are actually fixed point equations. I explained last time what was a fixed point. If I just have a function, right? Then, for instance, a function that maps real numbers onto real numbers, then a fixed point of f, x is a fixed point of f, if and only if f of x equals x. So the function maps the formula or the point onto itself. Now in our setting this is a little bit different because we don't have an equality but we have an equivalence. So we have formulas of the form f of x is equivalent to x, right? In my case, it's just written down the other way around. So what I write down is x is equivalent to f of x. Here is my x until, and here is my f of x on the right-hand side. Yeah. Good. Now, what is a special thing? A function in general can have several fixed points. So in particular, this equation can have several solutions. And the question is, which solution are we looking for? Yeah. So here in this setting, if you take the function f of x is something like, I don't know what, x squared plus 1, then, well, x squared is easier. Then the fixed points of this thing are, for instance, x equals 0, but also x equals 1 is a fixed point. Yeah? So this equation has at least two solutions, or in this case, exactly two solutions. Good, so we need to be much more precise about what actually the solution of these equations are. This is visualized again in this slide. You see that the formula on the left-hand side also occurs on the right-hand side. Good, so this does not yield, as I was just mentioning, a complete characterization. If you, for instance, take the last equation, this one, always psi or box psi is equivalent to psi and next box psi. The following two formulas are both satisfying this equivalence. First, plug in for the yellow part the formula false, okay? Then what you get is that false is equivalent to A and next false. Maybe you're a bit puzzled by the fact that I replace something with box by false. Think about this yellow part as just x, right? This is the formula that you plug into the equation. Right? So it can be any arbitrary formula. In particular, it can also be false. So if you plug in false here, then this formula says false is equivalent to f of false, which means psi and next false. And that's an equivalence which holds. But if you plug in box A, so you just replace psi by A, then also this equivalence is true. Yeah. So at least we have here two solutions to the last equation, the equation where you have the yellow box. So if we want to talk about box, we have to talk about which equation are we considering. Now in this case we have, for instance, let's assume these are all the possible solutions. Then what we are going to do is we're going to look at the smallest or the largest one. And what we are going to see in a minute for this equation, the last one, we're going to consider the largest one. The largest one in terms of implication, and that means in this case box A. Good, so box or box psi actually, you can also replace A by any arbitrary formula. Good. What is the critical point? Of course, that's obvious, I hope, that those two formulas, box A and false themselves, are not equivalent, but they lead to the same, let's say, you can plug them into the same equation. So what it turns out to be the case is that actually the two first formulas will be least fixed points and the other one will be the greatest fixed point. Yeah. So in this example, we have fx is x squared, we have two fixed points. If we just restrict ourselves to the domain from 0 to infinity, what is the smallest fixed point? The smallest fixed point is x equals 0. The largest fixed point is x equals 1. Largest with respect to what? Well, with respect to the ordering on the real numbers, which is just the ordering that you are all familiar with, the total ordering. What is the ordering that we're going to use here? We're going to use implication, or if you consider a formula as just representing a set of objects, which is the case, right? Because a formula has a semantics, a set of traces, then actually the ordering is just the subset inclusion. The subset inclusion in terms of the set of traces that a formula describes. Good. So the LTL formula phi until psi is what we call the least fixed point, the least solution of the following equation. Psi, this was my x if you want, equivalent to f of x, and this is f of x where you just plug in x at this specific place. Good. So the way that we showed this in the last lecture, and I will not repeat the proof, but I only will repeat basically the statement that we have shown, is that we did not prove this in the logical sense, but we looked at the set of properties, the set of traces, I should say, described by an LTL formula. So basically what we're doing, we look at the words of phi until psi. Yeah? Good. So if you then look at this equation and consider everything now in your mind as every formula is just a set, then I hope you see that this disjunction becomes just a union in terms of sets. This psi becomes the set of traces described by this formula. Okay? So what remains is how can we capture this in terms of a set? Yeah? So we do this as follows. We take something that satisfies phi, so we first look at the first conjunct. So that's weird. So we take an infinite trace satisfying phi. Now what do we have to do in order to satisfy the second conjunct? We have to express that the rest, so the next, from the next point on, psi should hold. Now if this is the sequence satisfying phi, what is then the next one? Well, the next one is by just erasing the first symbol. I mean, that's exactly what I tried to express here. You look now at the remaining sequence, right? So now the sequence is something of the form yeah, so this was my sequence, A0, A1, A2, A3, etc. What this formula says, okay, this satisfies phi, so this whole thing, yeah, this satisfies phi. And now I would like to express next psi. What does that mean? Next means from this position on. So I'm going to consider at the suffix starting from this position. Yeah. So I'm going to look at the suffix of A0, A1, etc. From 1 on, and that's of course exactly A1, A2, A3, etc. And I'm requiring that this suffix needs to satisfy the formula again. What does that mean in terms of, so it needs to satisfy the formula, well, psi here again. This we need to capture in terms of sets. So how are we going to do this? We're going to say that you look at the suffix A1, A2, and thus that must belong to E. What is E? Well, E is basically the left-hand side, which we kept it here as this E. So this is the set theoretical, counterpart of this psi. So I hope that this formulation, I got some questions afterwards, after the last lecture, that this is let's say, the set theoretical equivalent of the logical formula, which is on the top. Good. And what we have proven in the last lecture, and this is what I'm not going to repeat, because the important point is this least thing, right? So what we have proven actually is that the formula itself, because we want to show that this formula phi until psi is the least solution, we have transformed this equation into a set theoretical thing. So now we're looking at the least solution of this thing, of this equation. Again, it's a recursive equation because we have E, a set on the left-hand side, and E on the right-hand side. So it may have several solutions. And now we're looking at the least solution, least in terms of sets. That means we look at the subset ordering of those words. So basically, the domain is basically 2 to the power AP omega. And actually, we have sets of those things, right? And we look at the subset ordering. So least with respect to this ordering, the smallest set that satisfies the equation. And that's also the way we have proven it. We have proven that this set is the smallest set such that actually this equation satisfies. We slightly have proven a somewhat stronger statement, but that's basically the important thing. Good. Are there remaining questions about this point? The reason that I'm repeating this is that this expansion law is very important later on in the model checking algorithm for this logic as well for the logic CTL. And that means this is one of the, I would say, crucial parts of LTL. Good. So now I come to the second thing on the agenda of today. So far about the expansion law. And this is what we call the weak until operator. So what is the weak until operator? It's syntactic sugar. So it will be an operator that we can define in all the operators that we are already familiar with. But sometimes it's very useful. So this is the definition. Phi weak until psi is defined as being, well, phi must hold until psi holds. Now this part says that psi must hold at some point in the future. Now the weak thing is the second disjunct. It says, well, this weak is also satisfied if the first argument, that phi, holds always. Yeah. So whereas the strong until, or this until as we called it, insists on, let's say, establishing psi at some point, the weak until does not insist this anymore, because it says, okay, it's also fine if phi holds always. Good. So actually you can derive always and until also from weak until. So what does that mean? What I'm saying is the following. Our definition of LTL was something of the form phi is semantically something like true, an atomic proposition, you can have negations, you can have disjunctions, you can have next of phi, and you can have phi until phi. No? Or more clearly, phi 1 until phi 2. What I'm going to show you is that actually you can also define this in the following way. You remove this part and you replace it by the weak until. Yeah. This does not change the expressivity of the logic. It's just another basis, basically, to define the logic LTL. So how can you do this? Well, what we have done before is that in this scenario, what we did is we defined eventually phi as being true until phi, and then we were saying, okay, box of phi is not eventually not phi. And now what we're going to do, if this is the basis, we first start by defining box, and then we define eventually in terms of box. So basically we reverse the role of box and things. So how do we get box of phi? Well, that's not so difficult, right? Because you have this box of phi somewhere there. So this is something of the form phi until false. Yeah, because if this is false, then this until part will never become true, and then exactly it will get box. Yeah. And then you can also define until. How can you define until in terms of the weak until? Well, that can be defined as follows. Phi until psi, so now I'm insisting of basically having phi, so that means phi weak until psi. So that means phi until psi or always phi, and now we have to make sure basically that psi, we have to insist that psi becomes true at some point in the future, and that we do by adding this extra conjunct. Yeah? So I hope you see it's easy to define until also in terms of weak until. Good, what about weak until? Here is a small example, transition system with 3 states with atomic propositions A and B. Claim is this satisfies weak until B. How do we see this? Well, we have to consider the transition system, so we have to consider all possible paths. Okay? So there is a path that always cycles here, that never establishes B, but for the weak until this is fine because we have always A. And you see that for all the other computations, either you move here directly, which means you take this cycle 0 times, or if you take this cycle finitely often and then move there, you establish actually A until B. So therefore you have A, what they sometimes call unless B, weak until B. What about this formula? This satisfies AWB. Why is this? Well, there is only one execution of one path is maybe, going through this triangle in a counterclockwise manner, and that means that you always have A until B holds. What about this? Do we have A weak until B? Well, definitely if we go here, that's established because we have A until B, but this is the problem that if we now go to the right, we have a state that neither satisfies blue nor green. And that's always also the point that this is an example path that does not satisfy AWB. And therefore the transition system does not satisfy AWB. Question?
How would be the change for the first example if we change from the weak until to the strong until?
In the first example, if in the first example we would change this weak until into a strong until, the transition system would not satisfy this.
Okay, but how would you modify it that the transition system can still?
You would like to change the transition system. Yeah, but you want to establish a formula for a given transition system, right? So this transition system does not satisfy A until B because of this cycle here, where you never reach a green state. Yeah? So in order to establish A until B, you need to make sure that on every path you reach at least a green state by first only visiting a blue state. Yeah? Good. So here is a simple communication protocol, I think an example that we have seen before. If we look at this formula, blue implies blue until delivered. This is not true for this transition system. And the counterexample is the dashed path. So we move here and then we stay into this cycle, which means, okay, you are blue, you have also blue, but you will never establish delivered. But it satisfies the formula. It's always the case if blue holds, then blue, weak until or unless delivered. Because this allows you to also cycle around infinitely often there. That's no longer a counterexample anymore. Good. Actually, this is something what they call sometimes constrained liveness, and this is actually a safety property. If you look carefully at the W operator, it's this formula over here is a safety property. Good. The two ones are dual. And what do I mean by dual? And that's something we're going to use in the sequel. You can express the negation of an until formula in terms of the weak until, and vice versa. Okay, so we take the negation of an until formula. What does it mean to take a negation of an until formula? Good. So we take an infinite part again. This is my infinite sigma, right? Okay, what do we know? Sigma satisfies not phi until psi. So what could be the reasons that this infinite run does not satisfy this formula? Okay, now there are actually two possibilities. Either, what does this formula mean? It's the strong until, right? So you need to establish psi. So one possibility to not satisfy the formula, so this is of course equivalent to sigma does not satisfy phi until psi. How is that possible? Well, one possibility is that sigma will never establish this psi. So that means if phi holds here, if phi holds there, it holds phi at every state, but you never see a psi. Then we violate phi until psi. Good. What's another possibility? Another possibility is that you have somewhere you have a prefix where you have phi's, and then I would call it a gap. Yeah, so there is some kind of a gap. And the gap means that neither phi nor psi holds. Yeah. So this is not phi and not psi. Not phi and not psi. Psi. Yeah, not phi and not psi. And maybe then psi holds. That's okay. So this gap is also, I hope you see this, is making sure that you do not satisfy phi until psi, right? Because this is the problematic part. And that's the first disjunct. So the second disjunct was exactly the first scenario. You always satisfy phi, but you will not satisfy psi. So you never reach psi. And the second one is you have phi's. Here there are the phi's. But now until a point that is the gap, and the gap says, okay, phi, neither phi nor psi holds. Yeah? And these are the two only possibilities such that you can violate an until formula. Good. Okay, so I hope this equivalence is intuitively at least clear. If you don't, let's say, see the intuition, you can also prove this by using the semantics. It's quite a bit of work, I would say. So now we look at the shape, and now we do pattern matching with what is written down in the box here. So here you see this disjunction, or box something, right? Box something. And here this phi says phi and not psi, and this is exactly this phi and not psi. So you see, hopefully, immediately this is a W. Yeah? And this is phi and not psi, unless not phi and not psi. So here you see that the negation of an until formula can be mapped or can be expressed in terms of the weak until. Another way of saying this is that the weak until is in some sense the negation of a strong until, in some sense. Good. The same you can do with the negation of a W. So the negation of a W formula is equivalent to something with an until formula. So the duality goes in both directions. That's why the top of the slide says duality of U and W. Now what's the fun part about U and W? Now we have the weak until and the strong until. Now we can also look at the expansion law of the weak until operator. Yeah. And what it turns out to be the case is that both satisfy the same expansion law. Yeah. So this was the expansion law for until. Psi holds now, or phi holds now, and from the next position on, you satisfy the until formula. We have seen this was a fixed point equation, and what it turns out to be the case, that W is also a solution of the same equation. Yeah. So emphasizing again the fact that those fixed points equations can have several solutions, and phi unless, I call it typically unless psi, is either psi holds now, or then phi should hold, and from the next position on you have to establish phi W psi. Yeah. Good, this is the smallest solution, and the W turns out to be the largest solution. There are many solutions in between. You could define your own, let's say, version of the until operator. And some people did this in the literature, for instance, release, and this is also a solution of a similar kind of equation. So this is the largest solution. So this was until was the smallest property, yeah, and that's what you have seen. And what was basically W? So W is the largest property. It's the largest set of traces, such that, yeah, similar as we had before, the same equation holds, which means either psi holds, or, which was the union here, we have phi holds now, which means this statement, and then from the next point on until holds, and that next means was A1, A2, because we deleted the first symbol, and we were saying this must be an element in A. Yeah. Good. Okay. The proof of this last fact goes in similar lines as the proof that I did in the previous lecture for the statement about the smallest property. Good. So, bottom line, W is basically a kind of negation of until, and W and until satisfy the same expansion law. Good. This is the smallest solution, this is the largest solution, and this is in one slide the overview of all of them. This was the largest solution, right, the W. Remember that we defined box phi as being, what was it, phi W false. Yeah. This W, this is the largest solution, so therefore also this is the largest solution. That's one way to remember that box actually is the largest solution. Good, and these two things are the smallest solution. So this slide summarizes in one shot all the expansion laws for LTL. Okay, good. So how are we going to use this, the fact that W is a kind of negated form of until? Many people, for several algorithms, it's useful to bring LTL formulas into a specific shape. And the intuition is that negations are typically the complicated part. If they can occur at any point in your formula, then this may give rise to some certain complexity issues in the algorithms. So what many algorithms do is they basically restrict the positions where negations can occur. And the idea by positive normal form is that negations can only occur adjacent to atomic propositions. Yeah? So I can write down something like not A, but I cannot write down anymore not open bracket A until B closing bracket. I cannot negate an arbitrary until formula. That's syntactically no longer allowed. So the negation is only on the level of literals or atomic propositions, and it basically requires operations to be dual. So this is the syntax of LTL in positive normal form. We have true and atomic propositions. Now we only have negation to literals, so I also put false into here, because I can only put negations to literals. Then I have conjunction and disjunction. I have to put them both because I'm not allowed syntactically anymore to do negation of a conjunction. Yeah. So why do I need both? Well, this of course is the dual of this one, and that one is the dual of that one, right? Dual in the sense of if you complement them, you get something in terms of disjunction and negation. This is for propositional formulas. This, of course, is clear, I hope. Not true is false, and the negation of a conjunction is a disjunction. This is all known. So what do we have to do for LTL? We do the same for propositional fragment, but now we have to do the same for the next. So we need to do something with next of phi, and we need something that is the dual operator for next. What's the dual operator of next? So it's something that expresses the negation. But we have this law that says the negation of a next formula is a next formula where we push in the negation. And that means that the dual of a next operator is a next operator itself. So we don't have to change anything. Not for the next. So no need to add some operation, no need for next. So what about until? We need until, plus we need a dual operator for until, because syntactically we're not allowed to write down not A until B. So that's where we're going to use the W, because we have seen before the W is the negation of the until. Yeah? So here we see this again expressed, not phi until phi 2 was equivalent to, I think I wrote before, phi 1 and not phi 2, W not phi 1 and not phi 2. Good. So now we're going to see that actually the expressiveness of this logic is the same as for LTL. So in terms of the set of LT properties, or the LT properties that you can describe, these two logics are identical. Syntactically they are different, but expressiveness are actually the same. Good. There's no need to get eventually in box because we can still express them in terms of until and in terms of W. We can no longer define box of phi as not eventually not phi because that's syntactically no longer allowed. Yeah? But thanks of the W, we define it immediately like this. And now every LTL formula can be transformed into an equivalent LTL formula in positive normal form. So what do we have to do if we have to transform an arbitrary LTL formula into an equivalent LTL formula? Well, think about something like, I don't know what, negation A until B and not C, I don't know what, and not box C. This is not a formula in positive normal form. So what do we have to do? We have to push these negations in somehow inside. Yeah? Such that at the end we get a formula where only the negations are adjacent to the literals. So this can be done by a couple of, I would say, rewrite rules. So we have some rules that give an LTL formula as input, and the idea is that we get an LTL formula in positive normal form by successive application of the following rules. Now, some rules are pretty straightforward. So the negation of true, of course, is false. The negation of a negated formula is the formula itself. Here we have, of course, De Morgan. The negation of a conjunction is the negation of its parts and a disjunction. This was the law we had for the next. So a negated next formula becomes a next of the negated formula. And the until, the negation of an until becomes this W. Similarly, for the W, a negation of a W becomes an until. Now, you can easily now prove that this theorem holds, but what you see is that there is an exponential blow-up. An exponential blow-up because of the last line. The formula on the right-hand side is basically, almost twice as long as the formula on the left-hand side, and if you repeat this rule again and again and again, this formula will become exponentially longer. Yeah? Good, so let's look at an example. So suppose that we have this formula, don't try to interpret this, but just a negated formula. We don't allow negated formula, so you have to push the negation inside. So the first thing we do is we get rid of the first negation, the outermost negation. How do we get rid of this? By means of this rule. We push this inside by having this eventually. So that's what we do here. So this negation now becomes at this position. Yeah. The depth, yes, but you need to be careful because, I mean, these phi 1s and phi 2 themselves, they are negated here, right? So this can again give rise to a blow-up. I mean, depth, you mean here is one until formula at the top level in some sense, and here is a W on the top level. Yeah. But, I mean, if these formulas themselves are again until formulas, right? Phi 1 and phi 2.
But this shouldn't change the depth, right? Because we would still, so I see no transformation that increases the depth there. So if phi 1 has a depth of n and phi 2 has a depth of m,
that's not changing, yeah.
Then we would still have
But it's the point that this is I mean, not the depth, but the breadth is changing. So here we push the negation one level inside, okay? And now we have something of the form of disjunction. Now that's just De Morgan, so you can push this inside. So this becomes a conjunction, this becomes negated, that becomes negated. Now we can push this negation inside because the next operator has this law that this is equivalent to next not A or next not C in this example. And here we have a not A until B, and now we can use the fact that basically you can continue by replacing this by a W. So that's what I did here. So here you see that the until formula is changed into this W. Good. And this is the formula in positive normal form. Okay, the last part I like to deal with today is fairness. So I first briefly recall what is action-based fairness, and then we're going to see how you can model action-based fairness in terms of LTL. Good. So remember what was fairness. Fairness was all about removing certain behaviors that from some perspective or another one were not considered to be fair. And what we were distinguishing were three different kinds of fairness assumptions. Because there are different flavors of fairness, we said we focus on three different ones, which were unconditional fairness assumptions, strong fairness assumptions, and weak fairness assumptions. How did we define them? We defined them in the following sense, that actually a fairness assumption is a set of actions. Of actually a set of sets of actions. And we had basically allowed the arbitrary combination of those two things. So for instance, if you have a fairness assumption of the following form, so if the fairness assumption is something like, we have the F uncurled is something like a set that says alpha beta, and then we have another one which is maybe empty, and then we have the last one where basically we say it's alpha gamma, and maybe delta. Yeah, so then this is the unconditional fairness, this is the strong fairness, and this is the weak fairness. Then what does this mean? It means that from the unconditional fairness it says every run needs to visit alpha infinitely often, and it needs to visit a beta infinitely often. Okay, so infinitely often alpha, I write it down like this, infinitely often alpha. Alpha is not an atomic proposition, so therefore I put it in quotes. Plus, you have infinitely often beta in this case. What we were doing in the weak was saying, okay, you have to be weak with respect to alpha gamma. So that means, okay, if from some point on always, either alpha or beta, alpha or gamma is enabled, then we should take them infinitely often. Then infinitely often take alpha or gamma. And the delta was saying basically the same, but now we say, okay, if from some point on delta is enabled, then infinitely often delta is taken. Good. So then we said that an execution was being fair if it satisfies basically all the fairness assumptions in our triple. So that means that for all sets in the unconditional thing, in my example, the singleton set alpha and the singleton set beta on the left, it needs to be the case that you need to execute this alpha infinitely often. So there needs to be some position along the sequence such that we have such an element from A infinitely often. For the strong fairness, It means that the premise says that you need to have infinitely many positions where some action in A is enabled. So some state in your run, yeah, needs to be satisfying the fact that you can execute this action. I'm looking for my pointer, which it's here. Because you need to have infinitely many of those states in which you can perform this action. And then you need to take this action infinitely often. And with weak fairness, this was exactly what I explained, that from some point on, you only visit states wherein one of the actions in A is enabled, then you should take such an action infinitely often. Good. And then we defined the satisfaction relation saying that, okay, a transition system satisfies an LT property E under such a fairness assumption, so under such a triple, if and only if all the fair parts, so all the parts that are still remaining, so that are all satisfying the fairness assumption, all those parts satisfy the property. That means the trace of such a part is included in the set E. What I want to do now is I want to basically lift this whole thing to LTL. So the first thing is that one example of fairness, in which we call process fairness, is LTL definable. So of course we know what is LTL. So we have seen examples already in one of the previous slides. You can write down things like infinitely often a process in the critical section. And if you're awaiting infinitely often, so if process I is infinitely often awaiting, it will be infinitely often in the critical section. Similarly for weak fairness, if from some point on you are always waiting, process I is waiting, then infinitely often process I will be in the critical section. Now what's the difference with what I wrote on this, let's say, blackboard and the slide, is that these are statements about states, right? Whereas the statements here on the board are about actions that are going to be enabled. So there is some kind of mismatch between what is written down here, these are atomic propositions that are valid in states, and yeah, the action-based fairness assumption definition that we have introduced earlier. So LTL fairness assumptions are just conjunctions of the following form, and that matches exactly what I wrote down on the blackboard. Unconditional fairness assumptions that are of this form, eventually often, infinitely often, you do phi. If phi 1 holds infinitely often, then phi 2 must hold infinitely often. If phi 1 holds from some point on, then phi 2 must hold infinitely often. Good, and now we can define the following. So take such a fairness assumption. Yeah? So you take a formula of one of these three different syntactic formats. You pick a state in my transition system, and you have an LTL formula that basically my transition system needs to fulfill. Then we define the following. We say a state S in my transition system satisfies the LTL formula phi under the fairness assumption fair, the LTL fairness assumption, so under, well, basically a conjunction of these formulas, if and only if, similar as we had before, if and only if for all the parts starting in S, if the part is fair, then it needs to fulfill phi. Before I had something like the fair parts. I cannot define here the fair parts, so I have to define it in the following way, that if the part pi is fair, then it needs to fulfill phi. If it's not fair, I don't care. And that can be written down in terms of LTL as follows. So S satisfies under the LTL fairness assumption phi, if and only if S satisfies the LTL formula, if the fairness assumption holds, then you need to fulfill phi. So this slide is basically saying that all the fairness assumptions, all the LTL fairness assumptions, this fairness assumption here, can all be put into the formula. And that means that if we have a model checking procedure for LTL, so if we have an algorithm checking automatically whether a state or a transition system satisfies an LTL formula, I can also apply the same algorithm if I want to also check fairness. Yeah, because you basically push the fairness into the formula that you're checking, and then you're basically done. So here is an arbiter for mutual exclusion. So we have two tasks or two transition systems that want to enter a critical section. Then there is an arbiter that in the middle tosses a coin. So we get either heads or tails, non-deterministically, right? Then the parallel composition of the two transition systems with the arbiter looks as follows. Either, so they all start in the initial state. Then either the left one, I mean this flips the head, and that means that actually it can do an enter one. This enter one synchronizes with this enter one, and actually the first process, the process on the left, can enter the critical section, and then release the critical section, and the right-hand part is just a symmetric version of it. This does not satisfy the property infinitely often crit 1 and infinitely often crit 2. Why not? Well, it's possible to just go infinitely often here and, for instance, never go to the crit 2, to never reach this state. So maybe you want to impose a fairness assumption by basically forbidding this. So what you could try to do is you could try to find an unconditional fairness assumption, like this arbiter in the middle needs to be fair in the following sense, that it infinitely often needs to flip a coin and gets heads, and infinitely often it has to do tails. Then it's not difficult to see that the transition system I had on the previous slide satisfies under this fairness assumption this condition. And the way to see that is that this is the same as we have seen on the previous slide by showing so that's the same as saying T1 parallel T2 in parallel the arbiter satisfies the formula infinitely often heads and infinitely often tails, implies, and then the whole formula there, infinitely often crit 1 and infinitely often crit 2. That's equivalent to the formula we just have, we have here. Good. So, for instance, look at this transition system. Suppose that we have the fairness assumption if A holds infinitely often. I mean, if A holds from some point on continuously, then B holds infinitely often. And we want to check whether T satisfies next B under this fairness assumption, right? Then this is not the case. Why is this not the case? Well, in order to show that this is not the case, it suffices to provide a counterexample. So take this part. The first thing that we have to consider is whether this part is fair or not. Well, this is fair because there is no position from which always A holds. So the premise of the fairness condition is vacuously true. So this part is fair. And it does not satisfy next B because this is not green. Does it satisfy A until B? This holds. Why does this hold? Well, we need to establish first the fair condition, right? So from if A always holds like this would be a behavior violating A until B. But this behavior is not fair because it basically says that if you do A from some point on, then you also have to do infinitely many B's. And if you only cycle around between those two states, you never do a B. And so forth. So here is the third example. A until box B, if and only if next A. This is not true because we can find a counterexample. So the first thing is this is the part. The first thing is we need to check whether this is fair. This is fair because of the fact that the premise doesn't hold. We don't have a position where only always A holds. Then we have to check, so this is a fair part. Now we have to show that this fair part violates this formula. How can we see this? Well, this says that if B holds, if and only if next A holds. Well, here we have something where A holds, but the next position does not, we have A, but the previous position is not green. So this is violating the right-hand side of this box operator. Good. Those formulas can be necessary to prove liveness properties. This should not be a surprise because we have seen before that fairness assumptions are only relevant for liveness properties and not for safety properties. I think I'm going to skip this a bit. So actually what you have is the following result, which is a straightforward lifting to the result that we have seen before. Suppose I have a transition system T and an LTL formula which is characterizing a safety property. What does that mean? It means simply that the LTL formula, the set of traces that this LTL formula basically defines, is a safety property. If and only if this transition system under a realizable fairness assumption satisfies this safety property. What was realizable fairness assumption? It means that every reachable state needs to admit at least one fair execution. It's exactly the same result as we have seen before, but now in terms of LTL. Good. So here we have an example of a strong fairness assumption, infinitely often A and infinitely often B. Here we have a transition system which has no terminal states, so it fits the framework we are always considering. But this is not realizable because you see here that you get infinitely often A, but if you have infinitely often A, you have to establish infinitely often B. So this is a reachable state from which no fair execution is starting, and therefore this is not realizable. Yeah, so it's not the case that every LTL or every strong fairness assumption is, for instance, realizable, because this is a counterexample. Good. So the last part I would like to spend on going from action-based fairness to state-based fairness. Remember in this topmost blackboard, I was saying that eventually often, some action is enabled, and then infinitely often an action is taken. Now, these are not the atomic propositions that we are allowed to take into a formula, so these are not, let's say, LTL fairness assumptions already. So how is it possible to get from the fairness assumptions we are familiar with in actions in terms of LTL fairness? So the idea is relatively simple. We're going to introduce some new atomic propositions. So A, capital A, is a set of actions. And we're going to say the atomic proposition enabled A is true in a state. That's written down here. So the atomic proposition enabled A is true in state S, intuitively speaking, if and only if S has the possibility to execute at least one of the actions in A. So if there is an outgoing edge labeled with alpha for some alpha in A. Similarly, I define the atomic proposition taken. So a state S is labeled with the atomic proposition taken A if and only if for all incoming transitions of S, so all transitions that lead to S are labeled with some action in A. So intuitively this means if I am in state S, I know that I just have taken action alpha. And alpha is some action in A. Good. So then you can define basically the following LTL formulas, or LTL fairness assumptions. You can say, okay, infinitely often I have to do an action in A now means infinitely often I need to be in a state satisfying the atomic proposition taken A. Similarly, for strong fairness, you say I have to, if infinitely often an action in A is enabled, then infinitely often this should be taken. And the same similarly for the weak fairness. Good. Now, a small technical glitch is that, of course, if I have a state can have several incoming transitions, not necessarily labeled all with the same action. So here I have a state S. I can reach S via a beta transition, or I can reach S by one transition which is labeled by alpha. So how to deal with this is typically you make copies of the states. Good. So there are two alternatives. One is an ad hoc solution. I prefer the second alternative. We're going to do a systematic change of the given transition system. that you can fully automate, and then you can basically introduce those two atomic propositions, and you can cast every fairness assumption in terms of actions, then in terms of the new transition system. Good. Let's first look at an ad hoc scenario. This is a mutual exclusion algorithm with a semaphore. The semaphore initially is 1, and in some scenario, if you're in the critical section, it becomes 0. So now you would like to say something like enter 1 is enabled. So an ad hoc way of doing this would be you just look at the states in which enter 1 is enabled. These are the two gray indicated states over here. Okay, so they satisfy basically enabled with the singleton set enter 1. Now you would like to say when is enter 1 taken? Well, this is true in those two pink states, because those are the two states that you can reach by doing an enter transition. So this actually corresponds, and now what you try to do is you cast this, this atomic proposition, as you can see from the transition system, is equivalent. You would like to characterize the two pink states. Well, one way of characterizing them is by saying, okay, crit 1 holds, right? So this is basically the same in this example in terms of crit 1. Similarly, you can try to characterize the two gray states by saying, okay, I would like to express that you enter 1 is enabled. So what is characterizing the two gray states? Well, if you look carefully, they both satisfy weight 1. Now you have to be careful because this also is satisfying weight 1, but you don't want to characterize this state, so you have to add something. So you have to exclude this crit 2, and that you do by conjuncting it with not crit 2. Yeah.
Alpha has to be an A.
Yeah, which is here not the case. Yeah. Yes, because here, this is exactly the point. Here is a state that has two incoming arrows, one with the request and the other one with the enter. Exactly. Yeah. So this is why I call this ad hoc. Yeah. And my strategy would be don't do it this way. Yeah. Because then you can define something like this, but you have to be very careful because now you can also, this is basically, you can also enter this, yeah? But for this fairness assumption, in this example, this works, yeah? But not in general. That's why I call it ad hoc. Yeah? It's not a general procedure. Good. So that was the ad hoc way, the non-preferred way. So let's try to see to change the transition system. And the way to do that is if you have two or more incoming arrows labeled with different actions, you just copy this state. So you're going to add an action component to the state. So intuitively this works as follows. Suppose this is, here is my transition system. Now what we're going to do the following trick. We just do the following construction. So here you see that you can only reach, suppose it is the only incoming arrow for S prime. Then we're going to encode this beta into the state. Welcome. So what we do is we are going to take this, we're going to build pairs of states with actions. And the idea is that if you are in a state S prime beta, it means that you are currently in state S prime, and you have just taken the action beta to enter state S prime. Okay. Similarly here with S double prime, you enter it via gamma, so now I get a pair S double prime gamma. Good. So this means that on the left-hand side, we can express fairness in terms of actions. So here we would like to express something like strong fairness with respect to set A, and that means that in the right-hand side, after the transformation of the transition system, we are going to express this strong A fairness in terms of strong LTL fairness. And then we're going to say infinitely often enabled A implies infinitely often taken A. Good. How do we define now officially, formally this enabled A? So we're going to look at structures of this form. So all the states are pairs of the form S alpha. So this means I am in state S and I have just taken action alpha to enter state S. And that means that we're going to say that this state is going to be labeled with the atomic proposition enabled A, if and only if, starting, from S we have a beta transition, And here is the taken, which is the most important part, I think, that here you use the alpha. So here you say this state is labeled with the atomic proposition taken A, if and only if this action alpha that I just have taken is a member of the set A. Good. So this is how this works. So here is an example, and here is the example where you have a state S that has two incoming arrows, one with delta, the other one with gamma, which are labeled differently. That was the situation that was just pointed out. So what are we going to do? We're going to make a copy of this state. So first, you have to start somewhere. So I'm assuming that S, well, what is the action that we just have taken if we are starting in S? Well, nothing. Yeah? So the way to encode this is to say, okay, I add an extra artificial action begin, and this is saying I just start in S without taking any action before. Now you have to look at the transition from S to T. It's labeled with alpha. Now this is replaced by just again an alpha transition, but I replace the state by T alpha because I have just reached T via taken action alpha. I do the same for U, so U becomes U beta because U only has one incoming arrow over here. Good. Now we have to consider S. We can of course not reuse this state because this state was labeled with begin, and the next time you visit S, you don't visit that by doing a begin. So we have to make copies of S. How many copies do we need? Well, there are two different incoming arrows, labeled differently, that is the important point, and therefore we make two copies. So we make the copy S gamma and S delta. This is the transition you get to this S gamma, and now what we need to do is we need to copy all the behaviors of S into this state, right? Because S gamma can do all the behaviors that S can do. So this can do an alpha. So this definitely is able to do an alpha and move to T alpha, but it can also do a beta, and with a beta it can move to U beta. Yeah. So I get those arrows. Yeah. Again, from S I can do an alpha, so that's moving this alpha, or I can do a beta, and this is this edge over here, and then move to U beta. The same applies to S delta. Yeah. So this is the transition system I obtain after this transformation. Good. Are there any questions on this transformation? Any need for a formal definition, or you think that this is pretty clear, right? Good. Okay. So what's the strong fairness if I would like to express strong fairness for beta? Right, so here it's clear, then we just say, okay, we have a strong fairness assumption with the singleton set that contains the singleton set beta. Now we express this in terms of this transition system, and now we can express this by saying infinitely often enabled beta implies infinitely often taken beta, and that's basically the states that where beta is enabled are the three green states, because those are the only states that have an outcoming beta transition, the dashed lines over here. And what are the states that are taken beta? Well, those are the states where the second component of those pairs is a beta. So there is one state that satisfies taken beta, which is the pink state over here, and that satisfies the atomic proposition taken beta. So the message of this construction is that before we have seen action-based fairness on transition systems. If we want to capture this in terms of linear temporal logic, we have to do this in terms of state predicates. How can I transform the actions that I had before into those state predicates? By building pairs of states and actions. And then expressing this in terms of this enabled and taken predicates. Good. So here is the semaphore example that was mentioned before, how to do this, let's say, consistently on the example we had before. This is, I think, a fragment that I had before. So here you see the action, begin. This is the labeled request 1, so here you have request 1. I think here I omitted the label, but this is something like request 2, so there is request 2, enter 1, and so forth. So here you have those pairs of states on the original transition system and those actions. And now you see that I had to copy those states. That was the remark that was mentioned before. Here was the crit 1 way 2 that I can reach either via enter 1 from this state or via that state, or I can reach the same state, crit 1 way 2 y equals 0, by means of a request to. Yeah, so I basically copy the states if you are able to reach them by several actions. And now you can express the fairness assumptions that we have all seen before in previous lectures on the smooth exclusion algorithm, also in terms of LTL. Good. Any questions on this construction? No? Good. Okay. That's it for today. Thanks. Have a nice weekend and hope to see you back next Tuesday morning, 8:30. Thank you.